What if falling asleep isn't when your brain shuts down, but when its most important work quietly begins? Here on Relaxing Facts Studio, we explore the hidden science of the sleeping mind, where consciousness fades, but neural systems remain intensely active. While dreams come and go, deeper processes are reshaping memories, clearing metabolic waste, and maintaining the brain's internal architecture. In this calm, documentary-style journey, you'll step inside the sleeping brain to discover how dreams form, why deep sleep is anything but passive, and what your mind is carefully building while you rest. Dreams begin not as stories, but as patterns of electrical activity quietly igniting across the brain. During REM sleep, regions responsible for vision, emotion, and memory become highly active at the same time, forming coordinated neural networks that generate vivid inner experiences. The visual cortex creates images without light, while emotional centers add intensity and meaning, allowing the brain to simulate entire worlds with no external input. At the same time, the dreaming brain is not inventing content from nothing. It is recombining memory fragments stored across different regions. Recent experiences, older memories, and abstract concepts are blended together, producing scenarios that feel new but are built from familiar neural material. This recombination helps the brain explore connections between ideas, strengthening learning and integrating information without conscious effort. Neurotransmitters play a critical role in shaping how dreams feel. During REM sleep, chemicals like acetylcholine rise sharply, increasing neural communication and image richness, while others that support logical control remain lower. This chemical balance explains why dreams often feel immersive and emotional, yet loosely structured. The brain is active, but guided by internal chemistry rather than deliberate reasoning. Dreams are also sensitive to the outside world. Subtle sounds, changes in light, or physical sensations can be woven directly into dream content. A distant noise may become part of a dream scene, while bodily sensations are reinterpreted as movement or touch within the dream environment. Rather than shutting out reality completely, the brain selectively integrates external signals into its internal narrative. Together, these processes reveal dreams as a natural byproduct of an active, adaptive brain, one that continues to process information, explore memory, and respond to its environment, even while consciousness rests. Dreams are not random images drifting through a sleeping mind. They reflect how the brain and psyche continue working when conscious control steps aside. Early psychological theories viewed dreams as symbolic expressions of hidden desires, most famously proposed by Sigmund Freud, who suggested that dreams reveal unconscious motivations. Modern psychology, however, approaches dreams less as symbols and more as natural cognitive activity shaped by memory, emotion, and learning. One of the most consistent findings across psychological research is the emotional role of dreaming. During sleep, especially REM sleep, the brain revisits emotionally charged experiences in a quieter, less reactive state. This allows emotions to be processed without immediate action, helping the mind regulate stress and integrate feelings into broader memory networks. Dreams do not resolve emotions directly, but they provide a safe internal space for emotional adjustment. Dreaming also supports creative thinking and problem solving. By loosening strict logical rules, the dreaming mind explores unusual combinations of ideas that waking thought might reject. Many psychological studies suggest that this flexible mental environment allows the brain to test possibilities, generate insights, and discover new connections between concepts, functioning as a mental sandbox rather than a structured plan. Learning and memory consolidation form another key purpose of dreaming. As new information is absorbed during the day, dreams help stabilize and reorganize those memories. Skills, facts, and experiences are selectively reinforced, making them easier to access later. Instead of storing everything equally, the brain uses dreams to highlight what matters most. Taken together, psychological research suggests that dreaming is not a meaningless byproduct of sleep. It is a purposeful mental process that supports emotional balance, creativity, and long-term learning, quietly refining the mind while awareness rests. Deep sleep may feel like complete mental silence, yet beneath that quiet surface, the brain enters one of its most energy-intensive states. During slow-wave sleep, consciousness fades almost entirely, but oxygen consumption and metabolic activity remain surprisingly high. This apparent contradiction, low awareness paired with high energy use, reveals that the brain is not resting in the usual sense. It is redirecting resources away from perception and toward internal maintenance. In this stage, the cortex shifts into a highly synchronized rhythm. Large populations of neurons fire together in slow, powerful waves that travel across the brain. Rather than shutting communication down, these oscillations coordinate it, allowing distant regions to align their activity. This global synchronization creates ideal conditions for large-scale organization, ensuring that information processed during the day can be reviewed, sorted, and stabilized. At the microscopic level, another critical process unfolds. Through synaptic homeostasis, the brain evaluates the strength of countless neural connections. Weaker, less useful links are gradually reduced, while important pathways are preserved. This selective pruning prevents neural overload, conserves energy, and keeps communication networks efficient. Without it, the brain would accumulate noise, making learning and decision-making increasingly difficult. These combined processes serve a deeper purpose: survival of cognitive function over time. Memory accuracy, mental flexibility, and attention all depend on the brain's ability to reset and recalibrate itself each night. Dreamless sleep provides the conditions for this reset by prioritizing structure, balance, and efficiency over conscious experience. Far from empty or inactive, dreamless sleep represents a carefully regulated maintenance mode. It is a period when the brain protects itself from long-term decline, quietly preserving the foundations of thought, memory, and awareness without the need for dreams at all. Slow, rhythmic pulses begin to roll across the brain as deep sleep takes hold, not as random signals, but as precisely timed electrical events. These slow-wave oscillations emerge when large groups of neurons shift between active and quiet states in unison. Each wave reflects millions of cells coordinating their activity, creating a shared rhythm that defines the deepest stages of non-REM sleep. Rather than isolating brain regions, slow waves act as a communication system. As they travel across the cortex, they synchronize distant areas that rarely interact during waking hours. This timing allows information to be exchanged efficiently, aligning memory-related regions with those responsible for perception and reasoning. The result is not silence, but organized conversation, structured, slower, and optimized for internal processing rather than external awareness. This coordination plays a critical role in learning and memory. During waking life, new information is stored in temporary, fragile forms. Slow-wave oscillations provide the conditions needed to stabilize that information. By synchronizing neural firing, they support the transfer of memories from short-term storage into more durable networks. Complex knowledge, patterns, and skills benefit most from this process, becoming more reliable and easier to retrieve over time. The strength and quality of slow waves are not fixed. They are influenced by external and internal factors, including prior mental effort, environmental light exposure, and even ambient temperature. A day filled with intense learning can increase slow-wave activity, while disruptions in light or routine may reduce its depth. This sensitivity allows the brain to adapt sleep architecture to daily demands. Through these oscillations, deep sleep becomes an active communication state. The cortex is not shutting down, it is synchronizing, refining, and reinforcing the neural foundations that support clear thinking, stable memory, and cognitive resilience the next day.
Invisible decisions are being made inside your brain while you sleep. Decisions about what to keep, what to weaken, and what to let go. Throughout the day, your brain forms countless synaptic connections as you absorb new information, experiences, and skills. But not all of these connections are equally valuable. During sleep, the brain begins the careful process of synaptic pruning, identifying which pathways are no longer efficient or relevant. This selection process is guided by patterns of activity. Connections that were rarely used or weakly activated during waking hours gradually lose strength, while frequently used pathways are protected. Rather than deleting memories, the brain is optimizing its internal wiring, ensuring that important signals travel faster and more reliably. This keeps neural networks flexible instead of cluttered. At the same time, essential memories are being reinforced. Through a process known as long-term potentiation, key connections become stronger and more stable. Experiences that carried meaning, learning a new concept, practicing a skill, or navigating a complex situation are integrated more deeply into the brain's structure. This is why information learned before sleep is often recalled more easily later. Synaptic pruning also serves a critical efficiency function. Neural activity is metabolically expensive, and maintaining too many connections would waste energy and slow communication. By trimming excess synapses, the brain reduces background noise and prevents overload, allowing remaining pathways to operate with greater precision. Once pruning and strengthening are complete, the brain reorganizes what remains. Stronger connections are integrated into broader neural networks, improving how different regions communicate. Memory, attention, and reasoning benefit from this streamlined architecture. Rather than erasing the mind, sleep refines it. Synaptic pruning ensures that the brain wakes up not just rested, but better organized, prepared to learn, adapt, and perform with clarity the next day. A silent cleaning system activates the moment deep sleep begins, moving fluid through the brain with remarkable precision. Cerebrospinal fluid, or CSF, starts circulating along defined pathways, guided by a network known as the glymphatic system. This system uses gentle pressure changes created by slow neural rhythms to push fluid between brain cells, carrying away metabolic waste products that accumulate during waking hours. One of the most closely studied substances removed during this process is beta amyloid, a natural waste product of neural activity. During deep sleep, the movement of CSF becomes more efficient, allowing these particles to be transported away from active brain tissue. Rather than eliminating all waste instantly, the brain relies on consistent nightly clearance to maintain a balanced internal environment and support long-term cognitive stability. This fluid movement is made possible by subtle physical changes in brain cells themselves. As deep sleep sets in, neurons and supporting cells slightly shrink, increasing the space between them. This expansion creates channels that allow cerebrospinal fluid to flow more freely, turning the brain into a low-resistance system optimized for internal circulation. When wakefulness returns, cells expand again, and this cleaning mode gradually shuts down. Timing is critical. The most effective fluid exchange occurs during the deepest stages of non-REM sleep, when slow wave activity is strongest and external awareness is minimal. Lighter sleep stages do not produce the same hydraulic conditions, which is why uninterrupted deep sleep plays such an important role in overall brain maintenance. This nightly flush does not feel dramatic or noticeable, yet it is essential. By clearing metabolic waste and preserving a stable neural environment, the brain protects its ability to process information, store memories, and remain adaptable. Rest, in this sense, is not passive. It is an organized, fluid-driven process that keeps the brain functioning efficiently day after day.
Missing even a single night of deep, dreamless sleep may feel minor, but the brain immediately begins to show the effects. Short-term cognitive deficits appear quickly. Attention lapses become more frequent, memory recall falters, and problem-solving slows. Tasks that once felt automatic require extra effort, as the brain struggles without the restorative processes that occur during slow-wave sleep. Even simple decisions can feel mentally heavier when this stage is skipped. Over time, repeated deprivation compounds these problems. Chronic lack of dreamless sleep accelerates structural deterioration in the brain. Synaptic pruning becomes less efficient. Weak connections accumulate, and essential neural pathways are not reinforced. Regions responsible for memory, executive function, and emotional regulation show measurable decline, a subtle yet real form of accelerated neural aging that may increase susceptibility to cognitive disorders later in life. The consequences extend beyond the mind. Sleep deprivation disrupts the immune system and metabolic regulation. Inflammatory markers rise, glucose control falters, and hormone balance shifts, linking skipped deep sleep to a higher risk of infection, weight gain, and chronic metabolic conditions. The body's internal maintenance mirrors the brain's, both relying on uninterrupted cycles to function optimally. Behavioral and emotional stability is equally affected. Irritability increases,
stress tolerance drops and anxiety levels can climb. Decision-making suffers because the brain's emotional centers remain hyperactive while reasoning circuits are under-rested. Social interactions and workplace performance are subtly impaired, revealing how critical this restorative sleep stage is for daily life. Skipping dreamless sleep is not a minor inconvenience. It is a cumulative threat to cognitive efficiency, brain structure, systemic health, and emotional well-being. Protecting these nightly cycles ensures that both mind and body maintain balance, resilience, and clarity.
As night falls, the brain begins a carefully orchestrated journey through multiple stages of sleep, each with its own rhythm and purpose. Light sleep arrives first, a gentle descent where the body relaxes and the mind begins to disengage from external stimuli. Heart rate slows, muscles loosen, and the brain gradually reduces responsiveness, signaling the start of the nightly transition. Soon, REM sleep emerges, bringing vivid dreams and heightened neural activity. Despite this apparent mental liveliness, the brain is already preparing for the deeper restorative stages. Neurological markers show that conscious awareness fades progressively. Certain regions responsible for decision-making and sensory perception quiet down, while areas involved in memory consolidation and emotional processing remain active. It's a delicate balance. The mind appears asleep, yet intricate work continues behind the scenes. During this cycle, REM and non-REM stages interact seamlessly. Dreaming in REM allows the brain to process emotions and creativity, while slow-wave NREM stages reinforce memory and perform essential maintenance. The two stages complement each other, creating a continuous loop where experiences are integrated, skills are solidified, and neural connections are refined. Key subcortical structures, including the brainstem and thalamus, regulate these transitions. They act as gatekeepers, controlling sensory input and coordinating shifts between sleep stages. The brainstem suppresses unnecessary signals, while the thalamus fine-tunes communication between regions, ensuring smooth progression from conscious thought to deep restorative sleep. This nightly transition is far from passive. The brain is actively managing awareness, memory, and internal maintenance simultaneously. Understanding how consciousness fades and deep sleep emerges reveals the complex intelligence behind rest, showing that every night is a meticulously orchestrated journey that keeps the mind resilient, balanced, and fully prepared for the day ahead. Sleep is far from a passive state. It is the brain's most sophisticated nightly engineering project. While consciousness fades, a dynamic maintenance system activates, coordinating multiple biological processes simultaneously. Neural circuits are reorganized, weak synapses are pruned, and vital memories are reinforced. At the same time, cerebrospinal fluid flows through the brain, flushing out toxic byproducts and maintaining chemical balance. Energy resources are carefully allocated, ensuring the brain remains efficient and ready for the demands of waking life. This integration of memory consolidation, detoxification, and energy regulation transforms sleep into an active biological operation. The brain continuously prioritizes which connections to strengthen, which waste to remove, and how to optimize neural networks for efficiency. These processes work together seamlessly, highlighting sleep as a carefully timed, multitasking system rather than mere rest.
Every slow wave, oscillation, and rhythmic pulse contributes to maintaining the structural and functional integrity of the mind. Optimized sleep has profound implications for cognitive performance. Studies reveal that individuals who achieve consistent deep sleep demonstrate sharper memory, faster problem-solving, and enhanced creativity. The brain uses these nightly cycles to prepare for complex reasoning and adaptive thinking, laying the groundwork for learning and innovation during the day. Poor or disrupted sleep interrupts this engineering, leaving the mind less resilient and more prone to errors. Emerging research is expanding our understanding of sleep even further. Advanced imaging and neural monitoring techniques are uncovering how individual stages of sleep interact, how genetic and environmental factors influence efficiency, and how interventions could enhance restorative processes. Sleep is now recognized not as downtime, but as a critical, active system that sustains intelligence, health, and adaptability, shaping both our mental performance and long-term well-being.
Thank you for joining us on this journey inside the sleeping brain. If you enjoyed uncovering the hidden science of dreams and deep sleep, make sure to subscribe to Relaxing Fact Studio so you never miss a fascinating exploration. Help this video reach more curious minds by giving it a like and sharing it on your favorite social media pages. We'd love to hear from you. Leave a comment with your thoughts, questions, or insights from this episode. Your support fuels the channel, allowing us to continue creating calm, educational, and inspiring content. Together, we keep curiosity alive.